All right, hopefully you were able to figure out how to make yourselves an isosceles triangle just using an acute angle. So of course the technique was you just use a single compass setting. You're going to take this acute angle, you're going to use it as the vertex angle of your isosceles triangle, and you're going to turn these two sides of your angle into the two legs like so. You're just going to choose a compass setting. You poke your compass into the vertex of that angle, make an arc that intersects both sides, put some dots there, and then connect those two dots with your straight edge, and voila, you have yourself an isosceles triangle. Why does it work? The reason why it works is because this green arc right here, of course, is just a portion of a circle. We just draw the whole entire thing. What's the point of drawing the whole entire thing? But we know that it would be an entire circle. And the two sides that we marked as congruent would, of course, be the two radii of the circle. And any two radii of a circle would be congruent to each other. And so by definition, this is an isosceles triangle. Okay, so that leads us to our investigation of what we're going to call the Base Angles Theorem. The Base Angles Theorem, here's our Pons Asinorum picture once again, has to do with the two base angles of your triangle. So in this grayed out isosceles triangle here, of course, we're referring to angle B and angle C, all right? So for this little investigation, you already have one isosceles triangle that has an acute vertex angle. I'd like you to repeat that same construction, but this time make yourself an obtuse vertex angle, all right? And so the steps, again, just look like this. You draw yourself a vertex angle. This one is, again, an acute angle. On step number one, you can see that it's labeled with a point C, but you can choose an obtuse. I actually want you to choose an obtuse angle here for this one. You can label it C if you want to. Step two, you put the point of your compass on point C, and you make an arc that it's going to intersect both sides of that. Make some points of intersection. We'll call those 2 points of intersection, A and B, and then connect them with your straight edge. Make yourself an isosceles triangle. So again, our isosceles triangle this time is going to look like, hey, what's this? These are secret answers. These are secret answers. Get away from here. Okay, so if you're talking about an obtuse one, of course, this time it's going to look like that. And then you're going to have yourself some sort of circle that's going to intersect both sides of this. Let's see how good this thing does. Whoa, that's like perfect, right? And then it intersects both sides of this thing. That's assuming that that's the center. That looks more like the center here. And then, you're going to make 2 points of intersection in order to draw the rest of your isosceles triangle. Like so. Okay. All right. And now, once you have your isosceles triangles built with your compass and your straight edge, you got 2 of them to choose from. I'd like you to measure your 2 base angles here. So you can measure those things with a protractor. You have a protractor handy. Measure angle A, measure angle B. If we had ourselves a piece of patty paper, we could trace off triangle ABC, put angle A, just kind of flip your piece of patty paper over and put angle A on top of angle B, see how they compare, and maybe even have a piece. Maybe you swiped a few before you left class before the break. Awesome. Go ahead, break a piece out and take a peek at it, see what you come up with. Another thing that we could do is we could just take whatever piece of paper that we drew our isosceles triangle on, and we could fold it. We could fold it so that the crease goes through point C and puts point A right on top of point B here, and see what you notice about those 2 angles. So I'm going to pause right here, give you a second to investigate that. All right, so what you should have noticed, what relationship do you notice about the 2 base angles? It seems that these 2 base angles are congruent. The 2 legs are congruent, the 2 sides opposite them are congruent. And as a matter of fact, that's exactly how we're going to state this theorem called the Base Angles Theorem. Base Angles Theorem, what I want you to notice is that it doesn't have the word base angles in it, and it also doesn't have, it never even mentions the word isosceles triangle. Okay, so we're going to see how this thing is phrased. Please take some good notes here. Write down yourself the theorem and draw a picture to go along with it. So we've got, if two sides of a triangle are congruent, then the angles opposite them are congruent. Again, doesn't mention base angles, doesn't mention the triangles isosceles, but it doesn't need to. Okay, when it's the power of the theorem in this particular form is that it's very easy to apply it to an equilateral triangle, as we'll see at the end of this lesson. Okay, so how this theorem applies to this isosceles triangle, we have two congruent sides. This AB is congruent to AC, and AB is directly across from angle C, and AC is directly across from angle B. And so it's telling us that angle B and angle C are congruent to each other. All right, it is a theorem. Theorems are supposed to be proven, so let's set about proving this. As a matter of fact, we're going to prove it the same way that Euclid proved it. And here's his picture from the elements. And as we had talked about, this is referred to as the Pons Asinorum problem. And let's see if I can successfully guide you across this bridge so that nobody falls off. The way that we're going to do it is, as you can see in this picture, we have to add something to it. So here, let me just first explain some given and prove information. So we would be given, just like we see right up here, like this part of the statement, our if part, that our AB is congruent to AC. And that's it. AB is congruent to AC. And then we're trying to prove that the two base angles are congruent. Now, these two base angles were obviously just B and C, but there wasn't anything additional added to the picture. But this one, I've got some extra segments drawn in there, and we'll talk about why those things are in there in just a minute. But so I can't just call it B and C. So I'm going to have to refer to it as angle A. BC is congruent to ACB. Okay. All right, so essentially this is what it would look like. We would just have our unadorned triangle A, B, and C, and we'd only know these two sides are congruent. That's it. And we're trying to show that the two base angles are congruent. And you would quickly realize, as Euclid did, there's just not enough information. You need extra stuff in order to make this proof work. I mean, it seems so obvious when we're looking at our triangle that B and C is congruent to each other. We did some investigations. It seems so obvious, but as it sits right here in the picture, as it's given, there's just not enough information. We have to add some auxiliary segments, and this is what Euclid did. So he decided to extend out the sides of his isosceles triangle here, as you can see, to AD and to AE. And then he broke out his compass, stuck the point of his compass in A, and he made an arc that intersected both sides of his extended sides. This is exactly how we made our isosceles triangle, right? So he did it so that he could find 2 points F and G that were equidistant to point A up here, right? Which is going to give us the fact in a moment that we're going to use that AF will be congruent to AG. All right. Not only did he do that, then he connected those points back to the two base angles. So he connected C to F, and then he connected G to B right there. Okay, so we're going to see how the heck that was helpful. Before I do, let me clean up this picture because it's looking terrible. Okay, so this is going to turn into one of those type of proofs where we are trying to prove that some triangles are congruent to each other by like side, 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 side angled side, something like that. And in order to do that, we have to prove one set of triangles are congruent in order to get a second set of triangles are congruent. Let's take a look. Here's going to be our first set of triangles. Let's make them red. Our first set of triangles is going to go from F, A to C here. Okay. And just to make this easier to visualize, what I'm going to do is I'm going to trace this thing off. And then I'm going to move it off to the side so that we can just examine each one of these triangles in detail. All right, so it's going to be this red triangle here. Just move it over here. and its reflected image there. The reflected image is A, B, and G. Let me go ahead and label the points on this one. This is A and C and B. All right, excellent. All right, and then the reflected image here is A, B, and G. And let me move this thing over here too and label its points. All right, so I think this makes it a lot easier to visualize these two triangles and put some pieces together as what's congruent and how are these two triangles congruent to each other. So I've got an A here, a B, and this one down here is a G. And I think I mislabeled this one. Nobody spoke up. I'm pretty sure this is supposed to be point F. Okay. So we've got, from our given information right here, that AB is congruent to AC. Marvelous. All right. Also, because of the way Euclid constructed this, we also know that AF is congruent to AG by construction. That was his single compass setting that he used in order to find points F and G, right? So I'm going to mark that on there too, that these two are congruent to each other. What else do we have? We need a total of 3 pieces of information in order to prove that two triangles are congruent. Well, the other piece of information comes from taking a look at the original triangle and noticing that, of course, they both share angle A. It's the same angle on both of these triangles. So angle A is congruent to angle A by the reflexive property. And the reason why these two triangles are congruent to each other, as we can see, is side angle side. So that's what I'm going to write down next, is that triangle AFC is congruent to triangle A, make sure we match these things up, AFB by side angle side congruence. Okay, and then once the triangles are congruent to each other, then I know that everything about the triangles, all the other pieces that match up, also have to be congruent to each other. And as we'll see, these are the sets of pieces that we're going to need. We're going to need that angle F is congruent to angle G. Let me put 2 marks on this one though. And then how about FC? FC is congruent to BG. We'll write those things down now too. So angle F is congruent to angle G, and segment FC is congruent to segment GB by CPCTC. Now what the heck does CPCTC mean? Remember, go ahead, rattle it off. It's corresponding parts of congruent triangles are congruent to each other. All right, marvelous. Now, where did that bring us? Again, I don't think that we're any closer to showing that our two base angles are congruent. Or are we? So our next set of triangles that we're going to prove are congruent are the smaller white ones that are down here at the bottom, from FB to C and its reflected image. So just like I did before, just for a visual sake, I'm going to copy these things off. Here's the first one. It's purple. All right, I'll move this thing down here. All right, and then its reflected image. I'll copy that one. Oh, wait, hey, you're getting ahead of yourself. Let's label this FBC. Look how lovely this triangle closes off right there. Here, let me close that off a little bit. Okay, and then I'll trace off this other one here. And bring this one down to meet its friend. And this one was a B, C, G. And now let's mark the pieces that we had from our other proof as the whole reason why we proved those things were congruent. Like, for example, we have this right here that angle F is congruent to angle G. Let's mark those things in the picture. So So we got these two angles being congruent to each other. And then we also showed that FC is congruent to Great Britain over here. So I'll mark those as being congruent to each other. All right, and just like before, we're stuck. We need another set of pieces being congruent because we need 3. So going back to our original picture, what do we have? Well, notice that they shared BC. They share BC. That's common to both of them. Let's mark that on here. So BC is congruent to BC by the reflexive property. And so why are these two triangles congruent? Looks like they're congruent by, wait a minute, why am I using red? I need to be using purple. Make this thing match. Side angle? Oh, wait a minute. Side angle. Remember, we discussed this one in class. This is the one that it doesn't work. This one doesn't work because sometimes it makes 2 different triangles. It depends on the set of pieces that we have. So we can't guarantee that our 2 triangles are congruent if these are the set of pieces that we have. So it's just not enough. So that means that we need to go back to our picture and see, can we find another set of pieces which are congruent to each other? Well, what about the angles? Well, I can't use angle B and angle C that are here. Let me mark these in the original picture here. Just essentially because they're right below the original base angles that we're trying to prove are congruent to each other. Obviously, if the 2 base angles are congruent, then the angles that are right down below them are going to be congruent. As a matter of fact, that's what we're trying to prove right here. So we can't use those. We can't use those at all. And then likewise, we also can't use the tiny angles right there. We have no idea. We could show that they're congruent, but first we need to show that these 2 overlapping triangles down here are congruent. All right, which leaves us with these 2 pieces, BF and CG. Can we show that these 2 segments are congruent? And heck yes, we can. And the secret is in the segment addition postulate. All right, so let's get some things down here. So segment addition postulate, of course, means that if I take an entire segment, it's equal to the sum of its 2 pieces, like that, right? So that's what I'm going to do for both sides of this triangle in order to show that the 2 smaller purple pieces are congruent to each other. Okay, so we know from our given information that AB is congruent to AC. This means that AB is equal in measure to AC, right? That was given to us, and, well, actually it was given that they're congruent, so this is definition of congruent segments. Okay, and then we also had that the whole entire length is AF. This is right here by construction. AF is congruent to AG, which means that AF is equal in measure to AG. Also by definition of congruent segments, I'm not going to write it down again. It's the same exact reason. Okay, and so now we're going to use the segment addition postulate on AF and AG. So AF is equal to the 2 pieces AB and BF is equal to AB plus BF. And then we're going to do the same thing with AG. So AG is equal to, and on this one we've got AC plus CG. AC plus CG. This is good old-fashioned seg addition postulate. All right, and now by the transitive property, or substitution if you prefer, we can set these 2 things equal to each other right over here. Maybe change this color. Oh, orange. Will that look good? Probably. Those 2 pieces have to be equal to each other because we just said right up above here that AF is equal to AG. So AB plus BF is equal to AC plus CG. And again, that is either transitive property or substitution. I'll just write substitution here. Okay. And using substitution one more time on this bit that we have right up here, I can take my AB out and I can replace it with an AC because they're equal in measure. So I'll make that an AC plus BF. AC plus CG. The whole reason why I did that by substitution is so that I can notice that they're exactly the same thing, and I could cancel on both sides. I'm subtracting AC from both sides. So I'm going to subtract AC from both sides and get, finally, that BF is equal in measure to CG, and that is subtraction, which of course means that BF is congruent to segment CG. Whew, man. Pons Asinorum, I'm telling you. All right, so let's go ahead and mark that on the picture that we've got BF being congruent to, whoops, I guess I need to distinguish these three to CG there. All right, so now why are these two triangles congruent to each other? It looks like it's side angle side again, or we could use side 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 since we did already deduce that BC is congruent to BC. Which one do you want to use? Since I went ahead and showed that F and G were congruent to each other, the two angles, so I'll go ahead and use side angle side. Okay, so triangle, purple, triangle BCF is congruent to triangle, let's see, B would match up with C, C would match up with B, and then G by side angle side congruence. Which means that angle B is congruent to angle C by CPCTC. Corresponding parts of congruent triangles are congruent. Wow. All right. Are we done with this proof? No, we're not. We're sure not. We're just not done yet. No, because what we just showed, totally useful here, we just showed that this angle right there is congruent to that angle right there. Not even what we wanted to do, because we want these two angles to be congruent to each other. All right, the last bit of this proof then is using the linear pair postulate in order to show that our original angles, our original base angles, were actually congruent to each other. So, yeah, I got a little bit of space right here. I think I can still do that. So the way that I'm going to phrase this is angle A, B, C, plus angle, which we called angle B, so I can't call it angle B here. You know what? To make this a little bit simpler, why don't I just name these two angles? I'm going to call this one, I'm going to call this, stop. Wait, we need a different color here. We haven't used green. Nice. 1, 2, all of this is 3, and all of that is 4. So that's our B and C, that's right here. So would I say 3? Yeah, so 3, 3, try that again, 4 and 4. Okay, that's going to make it a lot easier for us to write these things down. Okay, so I've got the measure angle 1 plus measure angle 3 is going to add up to 180 degrees. Measure angle 1 plus measure angle 3 equals 180 degrees. Likewise, measure angle 2 plus measure angle 4 equals 180 degrees. And this is the linear pair postulate. All right, and I can pretty much stop right here. We've got two angles. No, actually, I cannot. I still can't do it. All right. So I can't set these things equal to each other. I can set them equal to each other by the transitive property or substitution. Measure angle 1 plus measure angle 3 is equal to measure angle 2 plus measure angle 4. Man, it seems like we've done this a whole bunch. This is substitution again. And speaking of substitution, that's this part that's right here. I'm going to substitute in a 3 for 4 or 4 for 3. Doesn't really matter because I'm going to get rid of it. Measure angle 1 plus measure angle, let's keep 3, I like 3, is equal to measure angle 2 plus measure angle 3. also a substitution. And even though I said that I liked angle 3, getting rid of them, going to subtract it from both sides in order to get measure angle 1 is equal to the measure of angle 2, subtraction. And if you prefer, angle 1 is congruent to angle 2, or as we stated way back here, angle ABC is congruent to angle ACB. All right, there you have it, folks. There is Pons Asinorum. Hopefully you were able to follow me. I hope that we didn't lose anybody over the bridge. I guess I'll find out in attendance when we return finally to school, or perhaps whenever we do our little online tutorial sessions, who made it and who didn't.